Next reaction I'd like to take a look at with you guys is nitrogen addition to aldehydes and ketones. So we're going to start off here with a methyl and an ethyl and a carbonyl sandwiched between them. So let's have here H plus, and then down here below I want to have a Z and H2. So this is the reaction that takes place with primary type amines, right? So the first thing that's going to happen is something that you probably predicted. You're going to activate, in essence, that carbonyl. So here you have your methyl, oxygen H, plus charge in your ethyl down there. And then like we've seen before, this gives us a resonance structure. So we're going to have here our resonance structure with a methyl, an ethyl, and an OH, and a plus charge there. So what we're going to see next here is we're going to see a nucleophilic attack. So we're going to come through here, and we're going to add here our Z and H2. So we're going to come around and we just do this. All right, so this reaction will take place when we have, again here, a Z. It usually is like an NH3 or a Z NH2. So that's for our primary amines. A secondary amine would have two Z groups on it, essentially. So like a Z2, like a CH32 NH, for example. We'll look at that down below. All right, so then what do we get here? We have our methyl, our ethyl, our OH, our nitrogen with a Z group, an H and an H, and a plus charge. And at this point in time, it's really just a series of proton shuffles. So we're going to go on here, and we're going to deprotonate that, probably with the base Z and H2. So grab an H there, and what that will give us is our methyl, our ethyl, our OH, and then our nitrogen ZH. We can write it out like that if we'd like to. So at that point in time, what we're going to do really is we want to get rid of our alcohol group, but we can't just kick it off right now because it would leave as hydroxide, and we're in an acidic solution. So instead, we're going to protonate this again. So you get another H plus in here. Okay, so swing around, grab that H. So that gives us our methyl and our ethyl and an OH2 plus, and then use your nitrogen with your Z and your H if we want to write it out like that. Now, remember what that did there is it turned this into a good leaving group. Okay, so then what happens is essentially that's going to leave. So we're going to continue down here. So we're going to boot off that water there. And then what you'll be left with is a methyl, and an ethyl, and then a nitrogen with a Z and an H on it. And then that group right there is going to end up having some resonance. And then we'll have a plus charge right down here at the bottom. And so with that lone pair in here, we're going to take that lone pair and come down right there. And that's going to give us our methyl and our ethyl here, a double bonded nitrogen with a Z on this side and an H over there and a plus charge right there. Okay, now the last step of this reaction occurs when we do a final deprotonation. So we're going to take that Z and H2 and do one more deprotonation. So come around and we do that. So that gives us our methyl and our ethyl, and then your nitrogen, and then your Z group over here. Right, your lone pair hanging out over here. Now this final product is called an imine. Right, so that's our final product for this. Now for a secondary amine, so if we start off with a secondary amine, right, so something like a methyl, an ethyl, an oxygen, but an H plus and a Z2 NH. Right, so without going through the whole mechanism, we'll just go dot, 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 dot here. As we go through, one of the intermediates that we're going to get is a methyl, an ethyl. Then you're going to end up with a nitrogen here, and you're going to have a Z and another Z over here. Right, and then a plus charge here. So in this situation, right, if you look above, it's essentially kind of analogous to that structure up here, except instead of having an H here to lose, there's no H here. So instead what happens is we end up losing H's from the shoulders, from our alkyl substituents. Right? So in this case, for example, if we were to look closer at it, right, that methyl is a CH3, we can write it as a CH2, an H, you have your carbon and your nitrogen here, right, with your Z group and your Z group, and then your plus charge down here. Right, now, and again, in this format here, you'd have your lone pair nitrogen, right? So that's why the positive charge is down there on the carbon. And then on the other side, that's an ethyl, so that's a CH2, so there's another H that could be lost, and a CH3. So both of those H's could be lost, giving us a mixture of different products. So why don't we just, for the sake of time here, let's just grab a hold of that H down here at the end. So if we were to continue down like this, you'd have your here your Z2 NH with its lone pair, and it would swing over and grab that H, and then the electrons would come down here. So you can see what we would form here is a CH2, double bond carbon, and then you got your two Z's here, and then this would still be your, in this case, it would still be your ethyl, right? So we'll write here plus other products because you could do your elimination over here. Now this product has a special name. It is a alkene next to essentially an amine. So when we put both of those together, this thing is called an N-amine. All right, now let's just take a look at the different situations that we can see in chapter 18. So the Z groups are just going to be different here. So if it's an R group, R, and H group, you have an amine or ammonia. That's going to give you an imine. Right, so here's our imine. If it's an OH, it's called a hydroxylamine, and you form an oxime. It's just the same idea. Mechanism is going to be the same, except that Z group is just an OH here. If it's an NH2, it's hydrazine, and you get a hydrazone at the end. And if it's NH connected to a benzene, you get a phenylhydrazine as your reactant, and a phenylhydrazone is your product. Now that carbon-nitrogen double bond, if you remember from our previous mechanism, we used reversible arrows. It can be converted back to the carbonyl by an acid-catalyzed hydrolysis. And that mechanism is just the exact opposite of what we saw in the forward reaction on the last page. Right, so kind of working through that a little bit, your nitrogen would grab an H. You get this protonated intermediate. Water attacks the plus charge. Right, H2O comes over, you lose an H there. That forms this carbonylamine, right? That's going to get protonated. Your nitrogen gets protonated. That turns this into a good leaving group, which gives you a carbocation that's in resonance with a form that's one proton away from your carbonyl group coming back. Now, side note about this too is that this reaction cannot be too acidic. So I wrote H plus in the mechanism, but if you have too strong of an acid, then what happens is that your NH2 gets protonated and it turns into a bad nucleophile. So it's a pH control reaction. So here, if we look at reaction rate, if we measure that as a function of pH, somewhere around 4 to 5-ish or so is your optimum pH for carrying out this reaction.